Hello and welcome to New York City Atheists, live on tape, brought to you by New York City Atheists Incorporated. I'm your host, Dennis Horvitz, the David Letterman of the Hopelessly Damned. And ordinarily, it's usually up to me to bring depressing messages, but I have a special guest who's going to basically help me out.
Good. I'll do what I can.
I know I can count on you, my guest. We are very fortunate to have Dr. Lawrence Kraus, who I'm not going to recite all of his accomplishments because we need a whole show just to do that, but he is the foundation professor in the School of Earth and Space Exploration and Physics Departments, Associate Director of the Beyond Center, Co-Director of the Cosmology Initiative, and Director of the New Origins Initiative at Arizona State University. Say that backwards 3 times. You have also taught at Yale.
Yes.
And he is, I don't have to tell him, he is the author of 7 books, including the bestseller, The Physics of Star Trek, and his latest book, Hiding in the Mirror, the mysterious allure of extra dimensions from Plato to string theory and beyond. I apologize for having to read my own handwriting.
It's difficult to do, I know.
And so basically all I really want from you is to take the next 23, 24 minutes to explain why shit happens.
Yeah, there we go. Okay, good. That's easy. It happens because it happens, but okay.
And thanks very much for watching. Bye. Yeah. Okay, basically, maybe we can kind of start at the end of your presentation today, around the, I guess what they call the anthropic theory.
Yes.
Could you just give a kind of a brief
Okay, sure. The universe has got certain characteristics that make it seem strange, in particular that make it seem like it's fine-tuned for life. Most of the recent interest comes around in a remarkable and inexplicable fact that most of the energy in the universe is in empty space. Empty space weighs something, and it's the dominant stuff in the universe. And that is so surprising and unusual. Why should empty space weigh something? That some physicists have turned to an idea that's cropped up periodically in the last century, and that is the notion that, well, why does empty space have energy? And maybe it's just because we happen to be here to observe it. Namely, if the energy of empty space were much greater than it is, then galaxies would never have formed. And if galaxies didn't form, then stars wouldn't have formed, and people and TV show hosts and things like that. And so we find ourselves in a universe that had that one parameter been different, we wouldn't have been here. Maybe there are many universes, and maybe all the parameters of physics have to be fine-tuned for life. And some, as I tried to say today in my talk, some people view that as a religious idea, but it's really not. It's really kind of a cosmic natural selection, because it really just makes a simple statement that life finds itself in a universe that can allow life to exist. If there are many universes, then there's some that don't allow life. Well, now, we don't even know if that's true, by the way. This whole principle is not really a principle, and it may just, we don't know if the laws of physics were changed that life couldn't form. So everything about the anthropic principle is very speculative.
Well, we human beings tend to think that reality is about us.
Yeah, exactly. Well, and this makes it seem like the universe is made for us, but it's quite the opposite, as I tried to argue. It's just that the universe is the way it is, and it's not too surprising that life evolves under conditions that it can evolve under. That's true on Earth, but maybe it's true in the universe as well.
Right. Okay. And I think another thing that they throw into the mix, at least in terms of the creationist argument and others, is the very fact they believe that the very fact of complexity implies a designer, and we know that that's certainly not the case.
Yeah, I didn't use the example today, but one that I often use in that regard is a snowflake is very complex and beautiful, but we know the laws of physics and chemistry and electromagnetism cause these beautiful snowflakes to form. And so the appearance of design doesn't mean there's design. And another example I give is, you might say, well, Buckminster Fuller's beautiful geodesic domes are human design, but in fact there's Buckminster fullerene, which occurs as carbon-60 in soot. And so it's not that, one shouldn't infer purpose and design just because of the appearance. And that's true with evolution, it's true for the universe in general.
Well, haven't there been experiments done that show that order can emerge out of what appears to be chaos?
Well, a snowflake is an example.
Right,
you cool water down, and under certain conditions it'll form a beautiful pattern.
Right. I guess one of the confusing, maybe even for me as a layperson, but I think one of the confusing conflicts, mental conflicts, is the idea that something can emerge from nothing.
Again, I talked about that today. It's
Yeah.
true. That's one of the basis, many people say the basis of religion. Why is there something rather than nothing? And in physics, we have an explanation. Obviously we don't have time today to talk all about it. I just gave a lecture on the subject, but it's really quite simple that all the evidence suggests the total energy of the universe is zero. And that's possible because gravity can have negative energy as well as positive energy. And laws of physics tell us that empty space is not so empty. Quantum mechanics causes fluctuations to happen all the time. And in a universe that's empty, a quantum fluctuation can create matter at the expense of gravitational energy, which is negative. And in fact, you're guaranteed that in empty space, eventually something will form. So there has to be something in some sense, just given the laws of physics. It's not too surprising.
So would it be safe to say there's no such thing as nothing?
Well, in fact, yeah, no, there not only is there such a thing as nothing, nothing is most of what there is.
Right. I mean, I have to tell you, I understand what you're saying, but I don't understand what you're saying.
Well,
I understand, but I don't
I'm
understand
sure
what you're saying. You know?
Yeah, well, unfortunately, at the edge of physics, all concepts are a little murky, but it's really kind of, none of us understand. It's the biggest mystery in science. Is why empty space has energy, and it's the biggest puzzle. And as I also said today, that's fine. Science is full of mysteries. That's what science is all about, is not knowing. It's not based on knowing, it's based on not knowing and trying to find out. That's what's exciting, and it's all right to not know things, and that's the difference between science and religion.
Right. I think others have said that to discover the unknown, to reveal the unknown, you go from what is known. Going from the known to reveal the unknown.
Yeah.
I don't. The idea I don't know, therefore, is illogical.
Well, yeah, but on the end, that's right. Although the other thing people don't realize about science is that what science is based on is proving things wrong, not proving things right. And as you keep getting rid of the wrong stuff, you hope that what's left over has some element of rightness in it.
You know, there seems to be there's of course, a lot of pseudoscience out there, as I'm sure you're well aware. And one of the misconceptions is that, especially say concerning the theory of evolution, is that the entire scientific community, of course, has collaborated to close ranks. That people who criticize evolution, or even from a philosophical basis, your point of view, that you're all getting together and conspiring.
Yeah, well, they don't. Again, that's a misunderstanding of science. As I've often said, most people don't realize that what every scientist does is wakes up in the morning and wants to go in and prove their colleagues wrong.
Right.
Not right, because that's the way you get famous. And so it's not as if people say, oh, that's a great idea, let's not consider any others. People accept the idea because it satisfies the test of experiment. And it would be great to find something wrong with it, because then you become famous. But in fact, evolution has survived the test of experiment and predictiveness for over 150 years.
So there's a greater likelihood, for instance, that if someone, say, came up with a scientific hypothesis that more or less effectively refuted the theory of evolution, is probably, rather than the entire scientific community closing ranks against it, is a better chance probably that someone would try to steal the theory and make money out of themselves.
Well, maybe, I don't know, money, fame maybe, or whatever. Yeah, I mean, if it's a better idea, people move to it, if it does a better job of explaining things. And like I say, there's much more evidence and many more scientific papers written suggesting that Newton's law of gravity is wrong than evolution.
Right. So basically, in the remaining time, what's going to happen to the universe?
It's going to get cold and dark and empty. The future of the universe, as I pointed out today, is miserable. We probably live in the worst of all possible universes for the long-term future of life. So much for intelligent design. The longer we wait, the less we'll see of the universe. The universe is expanding, and it appears to be expanding faster and faster. So the distant galaxies will move away from us and eventually become invisible. And that means in the far future, poor astronomers that evolve on planets around stars will look out and see nothing other than our own galaxy. They will not have any evidence for the Big Bang. They really won't be able to measure and see what's happening with the universe, and therefore that part of cosmology will be not only wrong but over in some sense. What I didn't talk about today is other things. The fact that we can see a limited amount of the universe, and the longer we wait, the less we'll see. Right. Also has negative implications for the future of civilization, how long civilizations can survive, how many computations you can do. And so, as I say, if the energy of empty space is the dominant stuff of the universe, then the future is miserable.
Right. And I guess that also means that, that should there be any intelligent civilizations in other galaxies, they're never going to know we existed either.
Probably not. I mean, I don't see that we're going to give much, you know, someone was asking me today, how can we leave a record? And I said that, you know, we don't have much of a record of a few thousand years ago, much less 50 billion years in the future.
Right.
So, yeah, I think our brief existence in the cosmos is something, as I like to say, we are completely insignificant, and that shouldn't depress us. We should marvel at the fact that in this random place in the middle of nowhere, we've evolved to have brains that have allowed us to understand the history of the universe back to the earliest moments of the Big Bang, to discover dark energy, discover evolution. And so rather than, you know, we may be insignificant, but the significance we make is our own.
Right.
The fact that we have a brain means that we should make the most of it and enjoy our brief moment in the sun.
Right, so that anything that matters actually is based on our own, I guess it answers kind of a rhetorical question. Does humanity want to survive? You know,
well, I don't know whether I'm sure humanity wants to survive. We have to start. If we're going to, I've argued that we have to stop. We have to accept the universe for what it really is. That the universe is the way it is, whether we like it or not. And until we accept that simple fact, our ability to meet the technological challenges of the 21st century will be remote, and the likelihood that we'll survive as a species will be less. We have to give up myth and accept the reality, empirical reality, and deal with it to solve the challenges of global warming and energy and all the rest. So
explain omega.
Okay, the omega, as I said today, omega, when physicists have an important number, they give it a Greek letter. Omega is the ratio of the actual density of matter in the universe today, divided by the amount you would need to make a flat universe. A flat universe is the boundary between an open universe and a closed universe. A closed universe is one which space closes in on itself. If you look far enough in that direction, you can see the back of your head. And omega measures what the actual density of the universe is. And if it's less than 1, we live in an open universe. If it's greater than 1, we live in a closed universe. If it's equal to 1, we live in a flat universe. And as I pointed out, for theorists, a flat universe is the only mathematically beautiful one. It's also the only universe that has zero total energy. So from a philosophical perspective, it's kind of nice because such a universe can arise from nothing. And we have now discovered, after a long and convoluted history, that omega is precisely 1. We live in a flat universe. And that was been one of the great developments of the 20th century, I think.
Right, because prior to that, there was the question of whether or not the universe is eventually going to collapse on itself.
Well, yeah, actually, although what I didn't get to say today, and I'd be happy to say now, is that unfortunately, that we've discovered that having just found out what omega is, that used to be, the reason I got into cosmology was to be the first person to know what omega is, and therefore the first person to know how the universe would end. But unfortunately, it's irrelevant. Turns out once you allow for the energy of empty space to be there, an open universe can collapse and a closed universe can expand forever. So omega is really irrelevant to knowing the future, unfortunately.
Now, there's you know, aside from our being insignificant, but to go back to what we were talking about before, there's a certain, we actually exist at a certain crux of awareness of ourselves and of the universe itself. Is that correct?
Well, we live in an unusual, what seems to be an unusual time. It's the only time in the history of the universe when the value of the dark energy and the value of the density of normal matter are almost the same. It wasn't true in the past, it won't be true in the future. And people are trying to understand that coincidence. It's a coincidence, and maybe it's significant, maybe it has to do with the laws of nature, and it's unexpected. But that doesn't imply that anything divine. So nature is full of unexpected events. In fact, every time we open a new window on the universe, we're surprised, and that's what's great about science.
Right, but I think you said if these values had come together, seemed to come together earlier or later, the whole would a whole different deal.
Well, certainly earlier, we know that if the energy density of matter and dark energy were the same much earlier, galaxies wouldn't have formed. And so we can say that's why we know that's not the case. If had that been the case, we wouldn't have galaxies and we wouldn't have us. Why it's not much smaller is not so clear. And so right now we just have vague arguments. We don't understand the nature of the dark energy until we have a physical theory. We won't be able to address this apparent coincidence. But there are lots of apparent coincidences in nature that are just sometimes accidental, and that may be of no significance whatsoever. People tend to ascribe significance to events that happens to them, as we kind of started the program with. Maybe it's a good way to round it up, is to end with the same notion as we began at the beginning.
Right. Well, that's deep.
Yeah.
That is very deep. The Big Bang. There's a. I guess that would come from. What was the term that you used? Fluctuation.
Well, I mean, it could be that our Big Bang arose from a quantum fluctuation in empty space. We don't know. The laws of physics that we understand that break down at t equals 0. So we again, it's just speculation right now. But it's certainly plausible that our universe, as we now see it, in some sense arose from the laws of quantum mechanics, which would be very satisfying to physicists because it would allow us, in some sense, to understand, address the question of why we're here from a fundamental physics perspective.
Right, but that's not again, the why we're here is
or how we're here, I should better
how
say.
we're here is probably
Science doesn't really address the why part. It really addresses the how part.
Right. It's not in any sense to be construed as supernatural or anything.
Yeah.
I mean, basically, science does not. It's not necessary for science to provide for any kind of supernatural explanation.
No, not only is it not necessary, it's anathema to science. Science assumes natural effects have natural causes, and then we try and understand the natural causes, and more importantly, we make predictions about the future, and it works darn well. And there's been no evidence that we have any need for anything beyond that notion. That doesn't imply there isn't anything, but we have no evidence of it, and so there's no that science. As I just wrote a piece in the turned out to be in the Wall Street Journal that Haldane, a very famous biologist, basically said, look, in my science I have to be essentially atheistic because I assume no one's coming down and fiddling with my experiments. And therefore I could see it's only intellectually honest to be atheistic in the rest of my life. But it's certainly true in science. Even if there is supernatural stuff, it's irrelevant to science.
Right.
And even if there were God, it would be irrelevant to science.
Right. That's. I know it's kind of irrelevant to me. But,
yeah. Well, I mean, that's just the way science works.
You gave an example, and unfortunately we can't reproduce it here, but you were discussing, going back to something you said earlier, about the space within an atom. How does that differ from a quark?
Well, quarks are in, well, what I was showing, I showed a picture, an animation of what the space inside a proton looks like. And there are quarks, 3 quarks inside of protons, but there's a lot of other stuff because the laws of quantum mechanics tell us that empty space, as I say, has got these bubbling brew of virtual particles and fields popping in and out of existence. And I showed a calculation of what the fields inside a proton look like in that empty space inside a proton. And I pointed out that the calculation suggests that those fields produce most of the mass of the proton. So these weird quantum fluctuations are really relevant for us to understand physics. It's not that they're just some metaphysical thing. They're really relevant to understand the properties of the universe, and that's very exciting.
And what is? Can you define a quark?
It's an elementary particle. That's that's one of a set of elementary particles with a fractional charge, that are the building blocks of protons and neutrons, and therefore of all matter in the universe. Whether they're fundamental, we don't know, but as far as we can tell, on our experiments, they are the building blocks of protons and neutrons. We never see free quarks. It's a remarkable property that the force between quarks appears to get stronger as the particles are pulled apart, unlike electrons, which gets weaker, and therefore it would take an infinite amount of energy to push the 2 quarks apart. It's an amazing theory called quantum chromodynamics. A Nobel Prize was won for it, and it's amazing, but it seems to be an accurate description of nature.
And it also provided the name for a Star Trek character as well.
That's a quark who I've been with on a number of occasions, and he and I are good friends.
Really? That's
yes.
great. That's great. And do I understand that maybe I got my information wrong here, but quarks come in and out of existence? Is that?
Well, quarks themselves. All elementary particles. They're real particles and they're virtual particles. So the real particles are around for a long time, and quarks, as far as we know, don't decay, but they may decay eventually. But quarks can pop in and out of existence at very small scales, as can electrons and photons and everything else due to the laws of physics. So there are these virtual particles popping in and out of existence. And then there are real physical particles that you can measure in a laboratory and hang around long enough to do stuff with. What it is true is that you can't get an isolated quark. Right. They come in this case in triplets or in pairs, and that's just the way it is.
Yeah, I just think people have trouble accepting the lay people have trouble accepting that on a quantum level, and just in general, because it's kind of counterintuitive.
The universe is counterintuitive, but that's what makes the universe interesting.
Right.
And we just have to change our intuition so it's not counterintuitive, and that's what science is all about.
Right. So you're not one of the you kind of refute the idea that scientists are just cold, rational people, and
they try to be rational. We try to be rational in our science.
Well, there's a time and place for everything, you know.
Yeah, human scientists are human like everyone else, and there's a time and place for people, you know. And scientists get carried away by ideas, and scientists make mistakes, and all of that is science is a human activity, and so, you know, mistakes by scientists should not be reflected badly on the process of science, because the great thing about science is those mistakes are finally found out. But hopefully I try and convince people that science is both fun and interesting, and that hopefully scientists are fun and interesting.
And it's essential to our survival.
It's essential to our health in the 21st century, absolutely.
Right. Whether or not there's going to be a 300 millionth century or not. You know.
Yeah, it doesn't matter. We only have what we have, and we better take care of it.
Right. I don't, Ken, how much...
Can I get some questions?
Well, I actually I'm going to have to go in a minute.
5 minutes, just 5 minutes.
Okay.
Thank
I
you.
have a couple questions. Can you describe what you think, how the Big Bang occurred? And
Good question.
And secondly, how do we know that the Earth is, the universe is 13.72 billion years old?
Well, we can. The great thing about the Big Bang is that we can measure it. We make some predictions about the universe. What's amazing is that everything we can see nowadays was once contained in the region smaller than the size of an atom. I wrote a book about it. It's called Atom. You should all buy it. And we don't make that assertion just a priori, because we can say if everything was once squished in an incredibly dense, incredibly hot ball, what would it have predicted? Well, we can, as the universe cooled down, when it was a second old, it was about 10 billion degrees. We can make predictions based on measurements in nuclear reactors and in accelerators, what light elements would have been produced in the early universe, and we find that 25% of the universe should be helium. When we go out and measure the universe, what do we find? 25% of the universe is helium. Then a little bit later, as the universe cooled down more, when the universe was 100,000 years old, we can predict that at that point matter became neutral, and there should be radiation left over from the Big Bang. When we look out, we see that radiation in the cosmic microwave background. So every prediction we make about the abundance of elements from hydrogen to helium to lithium we predict is 1 part in 10 billion. When we measure it, 1 part in 10 million. So our results are correct over 10 orders of magnitude. Every bit of data we have is consistent with only with the evidence of the Big Bang. So we know the Big Bang really happened. Now, if you were moving away from me in a car at 60 miles an hour, and I called you up and asked you how far away you were, and you said, I've gone 120 miles, I know you've been traveling for 2 hours. That's what we do with the universe. We measure galaxies moving away from us. We can measure their speed and their distance. And from that, we can work backwards and ask how long it's taken to get there. And when we do that, we come up with estimates of around 10 to 15 billion year old universe. Then when we try and actually make detailed measurements from our observations of that radiation from the Big Bang, we can refine that and ask how much it's cooled down and how far away that surface is. We could try and measure those things more carefully. And from that, it's really amazing that we've been able to determine the age of the universe, not to just between 10 and 15 billion years old, but actually a number of 13.72 billion years old. And that's truly an amazing, we should celebrate that as an amazing triumph of the human intellect and of the process of science.
Dr. Lawrence Kraus.
Can you talk about the concept of the candle?
Okay, the way we try and measure you might ask how do we know how far distances are? And after all, how far do we know how do we know galaxies are a certain distance away from us? We don't have tape measures. We use what's called a standard candle. I'm looking at this camera, I see a little light on the top of it. If I had a light meter here, if I knew that was a 10-watt light bulb on top of that camera, and I had a light meter here that said 1 watt, I could work backwards and figure out how far away the camera is, because I know light spreads out in a certain way. That's what we do with the universe. We try and find standard candles whose intrinsic brightness we understand due to the laws of physics, and then we look at them through a telescope. We see how bright they look, and we work backwards to find out how far they are away. And that's been a very hard process that's taken 80 years to refine, but now we believe we understand distances not to an order of magnitude, but rather to 10%.
Thank you, Dr. Lawrence Kraus. Thank you very much.
Thank
for
you very
taking the
much.
trouble
It's a pleasure. Take care.
You've been watching New York City Atheists live on tape, brought to you by New York City Atheists. Our guest has been Dr. Lawrence Kraus, a physicist and professor from the University of Arizona. And you know, we are broadcasting from actually taping from the Atheist Alliance International Convention in beautiful downtown Burbank. Please join us again next week. I've been your host, Dennis Horvitz. Thanks for watching.